The topic of today's paper reading is Route LLM, learning to route LLMs with preference data. This is a fairly recent paper. It came out towards the end of June, was subsequently revised in July. And already in a space of a couple of months, it has garnered a few research citations, 6 research citations. More than just being an interesting research paper, it has a lot of practical applicability. And I'll speak first and give the context to that practical applicability of what it has. Then once I've spoken to the practical applicability or the context of the problem it tries to solve, I will step back and give you an intuitive sense of how they go about solving it. And once we have an intuitive sense of how they went about solving it, then we'll carefully read through the paper. That's how we will proceed. So the problem is this. Today, there are models, large language models, of different degree of sophistication or size. We are aware that there is such a thing as a neural scaling laws. What the neural scaling laws say, and I will sort of simplify it down, what it basically says is that the bigger the model you take, the more tokens you train it with, the more compute cycles you train it for, the better the model becomes. But there is sort of a optimal point. If you have a small model and you go on training it forever, or you go on training it with a lot of token, you will reach a point of diminishing returns. You will reach a saturation point, right? Likewise, you can take a large model and you can go on training with just a small data set. And after a little while, you will reach a point of diminishing returns. Or so the scaling laws seem to imply, though recently there was the discovery of the grokking phenomenon. We covered that in a prior research paper reading, if you remember, in which all of a sudden there's a phase transition and a model which was more or less a big model, which was more or less memorizing the data or overfitting to it, suddenly generalizes it. But leaving those considerations aside, the broad context is that if you have a large model, you need a lot more data to train it with. And you need to train it for much longer. So the bigger the model you have, now in practical terms, there is a simple rule. Every time you download a model, a so-called model, what you're downloading are weights and biases, floating point numbers. Each floating point number is a 32-bit variable, right? It takes 32 bits, 4 bytes to capture that floating point number. Now, so suppose you get a 70 billion parameter model. You are all of a sudden looking at 280 gigabytes of space needed, right? And then there's generally overhead of loading the model, doing the computations, and so on and so forth, the forward pass, the inference path. So ready rule of thumb is to multiply it by 1.2. If you were to multiply it by 1.2, you realize that you're looking at 320 gigs approximately to run that 32-bit model, full unquantized model in all its glory. And that is still only a 70 billion parameter model, something like Llama 3.1 or something, isn't it? And in practical terms, what it means is if your H100 or A100 is 80 gigs, you're looking at least 4 of them in your machine. So to run these at inference level is, well, computationally expensive. But a model like Llama 70 billion parameter model, whether it's Llama or Qwen2 or any one of these, is still considered a middle of the line model. You have 2 choices. You can go small or you can go big. If you were to go big, now you're talking about GPT-4 class models, which obviously there's not much information revealed, but from what we can tell, they are approximately a trillion parameter size model. When you're talking about that trillion. So you're talking about 4 terabytes of VRAM that is needed. You can just count the number of GPUs that are needed just to run inferences on such machines. So those are obviously not something that you and I can put under our desk in a workstation, right? Or normal companies can afford to put. It is only the hyperscalers who can afford to have such large LLMs. Now, we do know, thanks to the neural scaling laws and the fact that larger models tend to have more abilities, that large models perform much better. The bigger the model, the more it has been trained, the more tokens it has been trained on. Generally, it's on benchmarks, it does very well. And in real life, it does very well. Right? On the other hand, you can go with very small models that you can fit onto your, for example, onto your 4090. You could go 2 billion parameters, you could go 7 billion parameters, and so forth. When you go to those smaller models, a given wisdom is that they don't perform as well. Right? I mean, people have been doing a lot of research to improve the performance of small models. Right? There has been amazing progress in lifting the performance of small models to levels that was considered impossible just a few months ago. And yet, these small models have done very well. Nevertheless, they are nowhere close to the performance of the strong or the big models. Right? Small models tend to get into trouble after a little while if the task is very complex. They simply don't have certain abilities well developed in them, especially complex reasoning abilities. Right? Their memory is literally smaller. Right? So how much they remember, the parametric memory is smaller. So what are the options that you can have? If you look at the history of this field, you find a slew of options. The most common option is quantization. Don't use 4 bytes. Don't use 32 bits. Use 16 bits. When you use 16 bits, people found that actually the performance degradation is not that much. Are we together? So if you have 70 and a 70 billion parameter model, let's say middle-sized model, you quantize it, you need 140, let's take 160. Yes, please.
Are you supposed to be looking at other pages? We're looking at the reference and citation.
Oh, yes. I am still having a general conversation. Perhaps I should change to this screen, this paper. No. So, no, I'm just making a general sort of what would I say? I'm setting the context, setting the stage for this paper still. So quantization helps. Now, if you have quantized, you realize that when you quantize down to 16 bits, it still works quite well, especially the 70 billion parameter model. Quantize it down to 8 bits, performance is still quite acceptable. What happens when you quantize down to 4 bits or 1 bit? I don't know if you have played with it. You'll start seeing that the model performance takes a noticeable dip, especially so for small models, 7 billion parameter, 2 billion parameter models. Quantization, at the end of the day, you have gone too small, right? And so quantization comes with its cost. It's not free. Go ahead.
Asif, the performance goes down in terms of the reasoning capabilities and
yes. By performance we mean the inference performance. Yeah. So the question from the audience is there a certain number of bits after which the performance degrades? So I can speak from experience. There's no like sort of a mathematical rule, but empirically we find that going from 32 to 16 is pretty fine. 16 to 8 is slightly noticeable. From 8 to 4 is very, very noticeable, right? You take a massive dip. And see, people have, the research community has even come up with an approach. They call it the 1.5 bit approach, right? They represent bit of information, floating point value, with either it is above 0, below 0, or 0, right? A 3-bit kind of a thing. And you can represent the 3 states with about 1.5 bits of information, give or take. People have done that and they say, hey, look at this. We still have reasonable answers coming out of it. Well, reasonable is in the eyes of the beholder, right? What one may consider amazingly reasonable, others may, in practical terms, not want to deploy in production. Right? So that's our current situation. So that is one way that people dealt with this. The other way that people tried to address this issue is using the mixture of experts approach. The mixture of experts approach says that you can sparsify the network by having a lot of small networks and just having a router in front of it, right? And this paper actually has some flavor of that. So I'll just draw it out for what it's worth. Now, mixture of experts is something we have been talking about in our community, but for the benefit of those, we are here for the first time. Let's go over it again. The basic idea is, suppose you have smaller models. Now, you know that smaller models will not be versatile and equally good at all the tasks anywhere within the shooting distance of a very large model. But what if these experts, each of these small experts, was very good at one task? If you just train it for one task, then it turns out that it can easily do comparable performance, give you comparable performance as a very large model. So I will just sort of, that's not the intuition, that's not how it works in real life, but just to convey the intuition, suppose I were to say that this guy, A is, A is good at algebra, A is good at algebra, and let's say that a B, again too thick, B is good at biology, and let's say C, where am I? C, and let's say C is good at chemistry, right? And while we're at it, let's throw in one more. D is good at dentistry, and so on and so forth, right? Then suppose a query comes, let's say that a query came to you. Here is a query. A user query comes. Suppose the query is, how do you solve a quadratic equation? So user A has this query, and there is another query. What is the difference between eukaryotes and prokaryotes? Prokaryotes, I don't know. I'm not a biologist, so I might have gotten the spellings wrong. So what you need is, let's say that these are the two things, and we will just take these two use cases. What do we need? See, the first one, this one, should somehow magically go to this algebra person, isn't it? And you do want somehow that this one somehow should go to the biologist, isn't it? So how would you do that? What you can do is, and this was the approach, this was suggested long ago actually in a landmark paper by Geoffrey Hinton, even before the LLMs came about. So what the great Geoffrey Hinton said is that, what if we have one more neural network? And this network was the routing network. And its only job is to just inspect the input and tell which of the experts it should it should delegate the task to. Does this make sense, guys? Right. So that's the basic intuition. Now, the technical implementation is a little bit more sophisticated. You typically give it to at least 2 experts. You hope that there are at least 2 biologists in the crowd and so on and so forth. And then you ensemble their results, right? But let's keep it to the simple intuition. So that is this whole concept that we have. This is called the mixture of experts. What we just talked about is called the architecture. This neural architecture has a name, mixture of experts. And how would you judge the quality? Like, what is the metric that will help you judge the quality of a routing LLM? It will be the correct routing. Given a query, it should route it to the correct expert. So in some sense, a routing LLM is a classifier, isn't it? Does that make sense? It is basically a classifier that you can train in principle with a negative log likelihood loss or something like that. Right? The standard classifier loss function. So that was another approach, because if you did that, what you could do is you need not have one ginormous transformer, a ginormous neural network, but you could have many small experts, little networks, and you could have a routing network in front of it, a feed-forward network or some sort of it doesn't matter what kind of a neural network it is, but you could have that a neural network on top of that. Now, with that as a background, now let's look at our problem. The problem statement is, and the way this paper goes about it is, and I'll sort of simplify it because we are first doing the intuition. So let's go with the intuition. Why am I not able to pen dark blue? Give me a moment, guys. This OneNote has a way to it is freezing up on me. All right, I'll just use this color. So there are, no, this is terrible. Give me a moment, guys. This thing does misbehave, and I have to sometimes stop and restart it. I hope I don't have to do that. Yes, let's hope this works. All right, so the framing of the problem that they're trying to solve is this. They say, let's imagine a world in which there are 2 kinds of models. A strong model, imagine a GPT or a Cloud or a Gemini class model, big model, and a small model. In reality, this paper is trying to solve the possibility of models M1, M2, MK, let us say, such that you can just imagine that this is a series of more and more and more powerful models. Now, one way to think about it is that the real world, the more powerful a model that you invoke, let's say you're using this service by calling Cloud or by calling Gemini or OpenAI, you're paying by the tokens, isn't it? Input token and output token. That is if you're using a cloud service. If you're using an in-house model, let us say that you manage to successfully deploy a large model in-house. There is still a query band. There's only bandwidth for so many concurrent queries to go to it, isn't it? So there are limitations. So we'll just take the commercial. Let's think in terms of cost per token and so forth. So bigger the model you take, the more expensive it gets, right? So then you ask yourself this question, if I If I were to get a question like this, let's go back to our own thing. How do you solve a quadratic equation? Is it a problem that a small model can solve? Or do I need the biggest, most powerful model? Or let's look at the second one, the biology problem. What is the difference between eukaryotes and prokaryotes? Right. Well, it's knowledge. Does it need a lot of reasoning, for example? It doesn't need a lot of reasoning. It's a knowledge, the answer is predominantly knowing the nomenclature. What is it that the biologists call eukaryotes, and what is it that the biologists call prokaryotes, right? Or vertebrates and invertebrates and so on and so forth. That is knowledge, not reasoning, broadly. So if you have experience with LLMs of different size, you can probably guesstimate that a weak model, a small model, would be able to deal with that problem very easily. In other words, this problem could probably be addressed by models in the smaller models, isn't it? It can definitely be answered by bigger models, but you would agree that it is somewhat cost ineffective to send this over to a big model, to send it over to, let's say, Cloud or to Gemini or to GPT-4, isn't it? So the question that it tries to answer is that here is the dilemma. Bigger models, so suppose I were to do this and I will draw a curve, which is not there in the paper, but I think is my way of interpreting it. So bear with me. Actually, let me make the X and Y axis like this. Too fat. Okay, I'll take this. Suppose this is the size of the model, powerfulness of the model, power of the model, size or power of the model, right? And what you're looking at is the cost. What does it cost? Suppose this axis is cost. And I'll just deliberately put one more axis, accuracy. You do know that, roughly speaking, there is some curve, and I don't know exactly how the curve will go. All I can say is that the curve will go something like this. As the model increases, the accuracy increases. Right. By the way, it's just a hand-waving argument, so don't take this curve too literally. Would you agree with that? That when it comes to accuracy, this is accuracy curve with respect to the size of the model. Unfortunately, the cost of the model rises alarmingly along a similar curve. The cost of the model is going up rapidly, isn't it? So the bigger the model, the more they charge you by the tokens, the better the model, right? And if you have a small enough model, let's say a weak model, it's practically free because you have it running on cheap hardware in-house, right? So the question is, if you know that a query can be answered by a smaller model, does it not make sense to route it somehow to a smaller model? And that is the crux of the question. A user input comes. From the user input, can we somehow infer what is going to be the power needed to answer this query? If we are reasonably confident that the bigger model is not going to give a materially better answer than a smaller model, then why not route it to the smaller model with maybe a marginal loss of a quality, right? A non-material loss of quality. So that is the question that this paper sets out to answer. Now, a little bit of a context of this paper. If you notice, do you notice that these are all Berkeley guys? These are also the people who are the people who created if you're familiar with chatbot arena, the LLMs chatbot arena, if you're not, I will just give you a quick demonstration. And for those of you who are familiar, please forgive me for this quick digression because I felt this digression may be worth getting into. What it says is that there are two models. You don't know what those two models are. So it's a blind study. You come here and you ask it a question, and it will, two randomly chosen models will answer your question. You get to be the judge, right? And it's been a fun game. This is how people have proven out their models because it's a very fair system. You can give them their model, they'll throw it into the arena and let the best model win, right? So there are over 100 plus models here. What is there any particular question that anybody would like to throw at it? How many hours in astronomy? Well, that's an easy one. Let's give it something. Okay, I'll give it something. Go ahead.
No. Does it rain in May in Oregon?
Does it rain in May in Oregon? Let's see. This is, you would, what do you, so let's think about it. What would you expect? Suppose model A and model B, one of them is a small model. One of them is a big model. Do you expect the answer to be materially different? Anyone?
Should not be, actually.
It should not be. Let's see. And here they are. Yes, it can definitely rain in Oregon during the month of May. While May is generally considered the start of the drier season, it is still transition. It is still a month when it can rain. Here are some details. Here's a general idea. So there you go. Both of them are giving you within the ballpark about the same answer, isn't it?
Yes.
Right. So let's call it a tie. And let's try something else.
So what were the models? Are they significantly, are they featherweight, or one is featherweight, the other is heavyweight?
Now, in this case, they haven't shown you which model it is, but if you're curious, I believe there is a way to ask it to reveal
one is Gemma, they say. Model B is Gemma 2.
Oh, yeah, here it is. Sorry, yeah, you're right. Right here it says. So it's Gemini 1.5 Pro, and the other one is Gemma 2. So you realize something, observe something very interesting. Gemma 2, which is a tiny model, Gemmas are by definition tinies, right? They are the mini Geminis, right? They come, Gemma here comes within ballpark of the Gemini. Gemini is the strong model, right? So if you were paying by the token and Gemma 2 is free and Gemini you're paying for, would you not like the ability to route your query to Gemma in this case? Isn't it? Now let's ask a slightly different question. And this one maybe
Jorge has an interesting question saying, can eternity be achieved? Ever be achieved?
Can eternity
ever be achieved?
Ever be achieved? Yeah, let's try that and see what happens.
There's a little bit of a reasoning involved here. Philosophy.
Yes.
Wow, they are writing quite a bit.
Indeed. And let's see what models there were. When we give the answer, it will tell us. So let's read through the answer. Physical eternity, biological immortality, this refers to living forever without aging or dying, etc. Cosmic eternity, the universe exists forever. Spiritual eternity, religious beliefs. Many religions believe in an afterlife, consciousness beyond death, some believe, and philosophical eternities, timelessness, etc. So in conclusion, whether it depends on how you define it, physical, spiritual. Let's see what this model has to say. is complex and can be interpreted in different ways depending on the context, whether philosophical, scientific, metaphysical, or theological. Let's explore these perspectives. Philosophical is often understood as timelessness, again, similar to what the other one said. Scientific perspective in science, especially physics and cosmology, time is often viewed as a dimension, much like space. Theories like Einstein's theory suggest that time is interleaved with space. This is actually a more precise answer as a person who actually worked in the theory of relativity and space-time. I am happy to see a mention of this. Can eternity exist in this context if the universe continues to expand? Yes. On the other hand, if the universe itself might have a finite endpoint, oh, this is lovely. This actually happens to know that just like there's a big bang, there can be a big crunch, right? There's an ending to the universe. Okay, theological, metaphysical, blah, personal existence. So in this one, would you say that B is, which one is better, A or B?
Wait. But the thing is, I know you're leaning towards B, Asif. But, I just heard of a concept called Elify today.
Elify.
Elify is explain like I'm a 5-year-old.
Oh, Elify. Okay.
Elify.
But we didn't say that. We didn't
say
that in the
but what I'm
prompt.
trying to say is from the perspective of landing in my head or somebody head, I think A seems to me
better.
Because there is a biological eternity. In this case, this B didn't even consider the biological eternity, actually.
Yeah. So I think it missed that one. You're right. So there we go. So see, at the end of the day, right, these perceptions are subjective. That's why these are called human preferences.
Yes.
Right? Human preferences.
I like B has done a much bigger, but I completely forgotten that aspect that A covered, which was the fact that physical forms and disappear.
That's right. So here's something very interesting. Something has come up with an answer which at least matches or is within ballpark of Gemini 1.5 Flash, an anonymous chatbot, which they haven't released. They haven't revealed. So you can assume that there's a new kid on the block.
Yes.
Right. And you could play this game once again. You could say, let's say, a new round. And the reason I'm doing this is this goes to the heart of what we are trying to do. Do we have a control on the model? No. Model A, no. Expand to see the description of the 74 models. We don't. So I'll just say, what are I am. Okay. Okay, we'll go there. Let's go there. What are globally hyperbolic spaces? So I'll just give because this was my first graduate school topic, so I'll ask this question. Let's see how the models do, and then we'll go over to the other thing. And I suppose doing this these experiments brings home the point of this paper. Wrongly causal Cauchy surfaces. Completeness. Actually, the best is the Lorentz metric M being global hyperbolicity. Both of them are tied because both have some part of the right answer. It's really interesting that a Llama 3.1, just 8 billion parameter model, is competing with a Mistral large. Right? So do you see, guys, what happened? A small model sometimes can be competitive to a much bigger model. Isn't it? In fact, I like this answer in many ways much better because it spoke to one most profound fact, which is that if the space is not globally hyperbolic, causality will get violated. In other words, you can go back and kill your grandma. Go back in time and kill your grandma. So globally, one intuitive way of looking at global hyperbolicity is there's no point messing in the space. No one point, so that you can't make a circle in space-time itself. Anyway, leaving that aside, what's the other website you mentioned? Zoom chat. Just spell it out. I'll have to search for it. I am. I am arena.ai. But am I getting it wrong? Oh, yeah, here it is. Yeah. It's the same thing, LM, arena battle. Oh, arena side by side. Okay, so here you get to choose. So let's do this experiment because this brings home the point of this paper. We'll deliberately take on the left-hand side a simple model. Let's take Gemma or Phi. What is the latest Phi? Phi is here. Phi small, Phi medium. Phi medium is pretty small model. Let's take that. Phi medium. And here, let's take GPT-4. Right? Now, this is David and Goliath, isn't it? This is your David and Goliath a battle. Let's ask the same question. What are globally hyperbolic spaces? And let's see how they do. And so when you look at this question, you can clearly see that GPT-4 did better, isn't it? Because the topic is pretty not commonly encountered. And Phi was trained on textbooks. Actually, it's a research topic. I can understand why. Should I? So now let's give another thing. Kanvi is asking, should I drive the autonomous cars? But isn't that a oxymoron? Yeah. How can you drive an autonomous car? Okay.
But I think it's a good one. Probably GPT-4 would figure that out.
Yeah. And the decision to use depends on various factors, including the level of technology. Autonomous cars offer potential benefits such as increased safety, etc. if you live in an area vehicle network. And this one perhaps gives you more details than you want. Right? It's a simple question. Somebody says, I'm seeing a Tesla will full whatever driving built in. What is that called? Full SD.
FSD.
Yeah, FSD. There, I have access to the key. Should I drive it or not? Is it safe? You just want an answer in simple terms, close to yes, no, and here's why. Right? So in this, would you agree that it is probably not worth paying the cost of this extra information? Isn't it? Now let's ask this question that I asked. How do you solve a quadratic equation? And let's see what this has to say. So it gives you multiple methods to solve a quadratic equation. And this just says to solve a quadratic equation, you would do factorization, 3 methods, factorization, completing the squares, and quadratic formula. Method 1, factorization, quadratic formula, and applying the quadratic formula, completing the squares. So it is giving you the same 3 methods, right? But with different degrees of depth. But I hope you get the point that at this moment, you're seeing the point. Sometimes you don't want to pay for unnecessarily detailed answer, right? Likewise, I can ask, what is the difference between, and for fun, I will just deliberately take a model let me clear the history. And because I can pick the model here, let me pick a mixture of experts. I talked about mixture of experts, right? Let's take a mixture of experts and compare that with, just to bring home the point that sometimes in-house mixture of experts might be enough. What is the difference between I hope I'm spelling it right, eukaryotes and any biologists? Yes. And good. They seem to be talking about fairly similar things, isn't it? Right? Short answer here on the left, pretty long answer here on the right, detailed answer. So you realize that big models tend to give better answers. But the question is, how much better? And that's the thing that this paper is trying to answer. So I'll first go over a simple version of this paper. They wrote a blog, which is this, and I'll go over this blog. See, look at the x-axis, which is cost. And the cost is in a log axis, which means if you move, let's say, from 0 to half, and then from half to full, you are incurring, your cost is rising exponentially. Right? So GPT-4 and Cloud, Opus, these are very, very expensive models. And they give you a lot of good accuracy, good model performance. Do you see? Models are performing very well in this particular thing. But look at tiny models, Mixtral, GPT 3.5 Turbo, Cloud, all the inexpensive models, small, inexpensive, weak models. What do? They cost much less, but their performances are not comparable. And what this paper suggests, which is that what if you had a router that could say, this problem a small model can solve, let's give it to the small model. This problem, most likely, the big model will do a much better job. And therefore, let's give it to the big model. If only we could do that, right? Ideally. So then you would have this so-called ideal router that you see in this picture, whose performances are within shooting distance of GPT-4. It's not saying that it will be as good as the best model, but most of the time, its performance will be close to that. And for most real-world situations, especially in enterprise environments, right, it will be good enough. But look at the cost factor. Once you realize that the cost along the x-axis is a logarithmic scale, you're talking of orders of magnitude smaller cost in many ways, right? So that's the hope that they are going for. So can it be done? Now the big question is, can it be done? And see here, they're saying the cost reduction is 85%, and while achieving 95% of the GPT's performance, which is ideally what you would like to see. So now let's go back and read the paper itself in detail. So I hope, guys, we get the intuition of the paper, right? Now let's read the paper. So this paper, which comes from exactly these guys, the chatbot arena guys, these Berkeley kids. So what they are saying is large language models exhibit impressive capabilities across a wide range of tasks. Yet the choice of which model to use often involves a trade-off between performance and cost. More powerful models, though effective, come with higher expense, while less capable models are more cost-effective. No brainer, right? We all know that. To address this dilemma, we propose several efficient router models that dynamically select between a strong and a weak LLM during inference, aiming to optimize the balance between cost and response quality. We develop a training framework for those routers, etc. So guys, we just talked about a mixture of experts kind of thinking. So now, with that kind of a background, you can think through and ask, can we, given a query, a very similar line of thinking, imagine that you could route, and this is what this paper will say, given a query Q, don't let it go. Instead, put a router network. Somehow we train it. It will answer only one question. And to simplify it, imagine that here is a big model, right? A strong model. It gives you strong performance. And there is a tiny model. And the question is, which of the two do you want to route it to? Because if you can solve it in the binary situation, then you can solve it. So one way, so how do you train a network like this? That's the whole question. And is it possible? Well, lucky for these guys, they were sitting upon the chatbot arena. They literally had a lot of queries, right? And which model did better? Strong versus weak model did better. Do you realize that? These guys were sitting upon the chatbot arena. Of all people, one of the things they have is quite literally this. They have a large corpus of queries and they have this two models duking it out. All you have to do is look at that subset of data in which a smaller model is duking it out with the larger model. Does that make sense, guys? So that is the sort of the organic data that has been accumulated. That is literally human preference data. Which of the two answers did you like? Or was there a tie? Right? So remember that what are the three states we observed in the website, in the arena? The three states that we observed is big model. So let's just look at it as the big model, M strong, wins, ties, or loses. Isn't it?
Mm.
So suppose you do a comparison in this situation and given a query and you have human preference data in this. Now, what they did is they augmented this data using two different techniques. So this data set that they were sitting on, they augmented this data set. So let me just put the intuition here. The arena data set, which is human preference data set of models A versus B, right? All you have to do is pick places where A or B, one is strong, one is weak, right? Now you have the data, you take this data, use some augmentation, then you can create more queries and then ask another LLM to judge which was the two response that was better. Use all sorts of techniques to finally create a training data set, create a sufficiently large data set to train the router. Now, how would you train the router now? You have this data set. All you know is this was the query. This is where the big model won. This is where the big model tied. And this is where the big model lost. Isn't it? That's all you know. So you need to now put it into a more mathematical framework. So the mathematical framework they put it in is it's sort of dead obvious and very beautifully written here. Very clear language they have written it. So I'll just read it out to you. And what they're saying is, consider a set of n different models. By the way, when they say n models, right, for the sake of our argument, just assume two models, right, big and strong, because from there you can generalize it. Each model MI, for each model MI, given a question, they call it Q, maps to an answer. That's what a model does, right? Any model MI will map a query to an answer. I should have said A. QA. A question is mapped to the answer that model would give, right? So that's what they are saying. Each model, MI, maps a question, is abstracted as a function that maps a query to an answer. Therefore, a routing function, and this is the important statement, a routing function R is an n-way classifier that takes a query Q and selects a model to answer the question. So what you are really searching for is a routing. We just said that we read a routing network. But remember, in neural network theory, a network and a function are the same thing because the whole neural network is nothing but a function. It acts on the input to produce an output. So what do we want our router, this routing function, routing network or function in mathematical term, because a network is nothing but a function. What do we want this function to do? We want this function to do this mapping, to go from given a query, right? And given a model, given a query, it should be able to, a model to answer the question. It should be able to tell which of these models should answer the question, M1, Mn, right? Or simply put, the way I made the diagram for the binary case, strong model or the weak model, right? The challenge of routing involves achieving an optimal equilibrium between increasing response quality and reducing cost. So you realize that there are two opposite forces. You want to improve the response quality, it comes at a hefty price. You want to reduce cost, you lose quality. So you have to find an inflection. You have to find the sort of what I would call, let me, if I may use a word, you're looking for the Goldilocks region. Isn't it? A place at which the cost is not too high, but the performance still is awesome. Right? As far as human beings are concerned, they still feel the performance is awesome. The model is doing that, the whole network is doing the job. That's what you would want. So that's what they are saying. The challenge of routing involves achieving an optimal equilibrium between increasing response quality and reducing cost. Assume we have access to preference data, which in their case, they very much have. Now, what was the preference data? Given a query, Lij is a label representing the comparison outcome of comparing model I and model J. That's literally what we did. So they are saying, assume that it is so. Well, the reality is they do have it, right? These authors have it, but they're putting it in a mathematical language. Now, they make a point. It is important to distinguish between reward modeling and routing. They're saying that, see, it's not reward modeling. Reward modeling evaluates response quality post LLM generation, right? So if you're doing like which model to reward, right? You will have to generate the output and then do it. Whereas here, the question is you don't produce the output. It's expensive. You route it to the right one. That's it. So in other words, it's more a classification problem in simple terms, right? This necessitates a deep understanding of the question's complexity as well as the strength and weakness of the available LLMs. So what you're saying is, what the router is doing is two things. It is not only trying to understand the complexity of the question, but one important point that people tend to miss is big models are not necessarily better in everything. If you're comparing model A and model B, A may be better at 10 things, B may still be better at 2 things or 3 things. Are we getting it? And so one of the jobs of the router as it gets trained is also to learn the strengths and weaknesses, the comparative strength and weaknesses of the two models for different kinds of problems. Right? So that is an important point, because let us not assume that all that the network does is inspect, routing network does is inspect the complexity of the question. It is looking at the complexity of the question contextualized to the strength and weakness of the different models, the different LLMs. So how would you do that? The win prediction model. So let me just jump ahead and say, see, suppose I say that given a model, the probability, given a query, let me use a less thick pen here. So go along with me here. So you're given a query. So the word given is represented with a vertical line in math and thing. So what does it mean? Given Q or condition.Q or Q, right? Given Q or condition Q. What we want to do is find out that win. So I'll just take win probability of winning, right? One of the three things. Strong model wins, ties, or loses. For each of these, given a query, all you can have is a model. Machines just come up with probabilities, right? Machine learning in predictive analytics, like if you do a classifier, what do classifiers produce? The probability. So you would agree that it can only find these three probabilities, right? So let us say that I took query I, a particular query, Q, and this was it. So the probability, and let's say that in that particular query's case, the real answer was, let me say that the real answer was the big model wins. I'm just taking it hypothetically, right? Or you could take the big model loses. It doesn't matter, or ties. It doesn't matter which of the three cases are true. So the machine will come up with a probability. You know that it won. So now, if you have to quantify the loss, how wrong was the model? If the model said 100% sure, big model wins, then the probability is 1, isn't it? And how much mistake has it made? No mistake, right? Zero mistake. So one measure, one intuitive idea of loss is that it is the log of this. Because if it said 1, it would be 0. On the other hand, if it said 0.1, the loss would be quite high, isn't it? Right? In fact, you would try to minimize. In fact, many of you remember this as negative log loss, right? So the intuition is you want to, if loss functions you try to minimize, for some reason they wrote it as a maximization problem, but take away the minus, it becomes a maximization problem. What you want to do is you want to make sure that this machine predicts as high a value for this probability as possible. And if it comes up with the lower value, you want to penalize it. Are we together? Right? So min of the loss is the same as max of the, without the negative sign. So log P. And let me just take this one, wins versus Q. I'm just taking it like this. Does that make sense? So do you see, guys, that this loss, the win prediction model, the job it has is quite simple. It has to maximize the likelihood on the preference data. Guys, common sense, right? This is basically your classifier kind of a thinking. So we do that, but there is a problem. If you just try to make a machine that increases the likelihood of this function, right? Guess what it will do? You happen to know that the strong model mostly wins, isn't it? And so one trivial solution that it will come up with is to say, route all the traffic to the strong model, because then your error rate will be very low. Are we making sense? Right. So that is a degenerate case. You don't want it to do that. That will defeat the whole purpose, because there is another factor that you have to look at, which is the cost factor, right? It's a cost threshold. You have to say that, see, here is the main parameter, the alpha. You say that if the probability of winning, right, winning of the model is less than, you take a value. Let's say that I take a value 50%. There's only 50% chance that the strong model will do better. Why not route the traffic to the weaker model? Or even more extreme. Let's say that alpha is 0.1, right? Or 0.01, 1%. If alpha is 1%, the probability that the strong model will do better than the weak model is just 1%. What does common sense say? Most likely this weak model will do just as good, isn't it? Maybe even better. So you would rather route it to the smaller model because your cost will be less, right? And so alpha, in some sense, is your threshold. It controls how much are you willing to sacrifice, right? If you set alpha very low, then you are being like very stringent, you're incurring a lot of cost. If you make alpha, if you're saying that the machine needs to be 90%, like there's a 90% chance that the strong model will outdo the weak model, then only send it to the strong model. You'll have a lot of cost saving, isn't it? So alpha is the threshold that controls what level of cost savings you have. What's a trade-off between cost saving and uh, quality of your responses in some sense, right? So those of you who are familiar with classifier theory, you might remember something similar that used to somewhat, it rings a bell. Like do you remember the precision loss, the precision and recall curve, or the area under the ROC curve? Like at what percentage, in a classifier, if you have a probability, where do you put the cutoff? And based on the cutoff, how much false positive and true positives you take, etc. So there is a flavor of that. If you look at it, these curves, do you notice that well, I won't go into it because many of you may not know about the ROC curves and so forth. But in any case, there's a flavor of that. Then it goes through some mathematics, which I'll skip. But the bottom line is it looks at the accumulated, especially if you look at this, you will see that it sort of does, to me, it had a strong echo in some sense, very like vague echo of something like the area under ROC curve when I saw this integral, right? It's sort of like that. And the graphs also are like that, but I won't go into it. So they have 4 methods to train the router. One is a statistical method. It's an old method, a similarity weighted ranking. It goes back quite a bit. Then the next is a more sophisticated method is matrix factorization. Now, matrix factorization, if you remember, should be reminiscent of a recommender system. If users, like let's say in an e-commerce situation or Netflix, it got popularized because of the Netflix prize way back 20 years ago. The problem was, if there are so many million users and there are so many 100,000 movies or shows, this user liked that show or watched that show or that movie. Based on that data, can you come up with telling me which movies to recommend to which user, right? Or which items to recommend to which user. So basically the axes are a user, item, right? So user may have, for example, many users, a user, and items may be, users may be A, B, C, D, E, F, G, and items may be alpha, beta, gamma, delta, epsilon. Now, this user, D, may have just bought and liked this one. And this user may have liked this one, and this user may have liked this one, and this user may have liked this one. This is the kind of data you get. And they may even have a rating number, thumbs up, thumbs down, 0, or something like that, right? Or maybe 5, 3, whatever it is. And your job is to fill up the rest of the matrix. And what the matrix factorization essentially says that there is a lower dimensional space, an embedding space, a taste space, what people often call it, low dimensional representation, says that the user is a vector in that abstract taste space, and an item, user is here, and an item also, there are items all around the user. They also can be projected into the taste space. And what item would you recommend to the user? Just look at the items around the user. Those are the movies the user is most likely to see or like, right? So that was the matrix factorization problem. So they take this problem and they convert it into a matrix factorization problem or a recommendation systems problem. How do they do that? And so that's what they say, inspired by matrix factorization models in recommender systems to capture the low rank structure. Low rank structure is just low dimensional space, taste space, of user item interaction. We leverage this approach to train on preference data. The key is to uncover a hidden scoring function, S. So all you need to find, guys, in recommender system is a scoring function that says, given a user, given an item, exactly how much will the user like this item, or what is the score the user will give to this item in the situation that the user happens to watch this movie or this show. Right? That's the only question you want to answer in a recommended system like this. Does that make sense? So they map it to a scoring function, represent the quality of the model's answer, etc. So P-win, you can write it like that. I won't go into that. The next approach is BERT classifier. BERT classifier is a no-brainer, right? If you remember, just to whet your recollection, what does a BERT do? BERT is a transformer such that given the input, you prepend the input with a query. So this is your query text. You prepend it with a CLS token. When all these things get the contextualized vectors, the hidden state vectors come out of the BERT transformer, you in particular look at the hidden state of the CLS token. If you remember the old BERT theory. So this is what you get. And so all you need to do is you need to just ask this question, winner or what's it? You just have to pass it through something like a sigmoid function, a logistic regression function to say, what's the probability that the winner, right? And what do? You just pass it through one more transformation plus B multiplied by one more weight matrix, right? Plus B, and then you feed it into a sigmoid, right? A logistic regression function. Remember logistic regression, right? So let's say that this is Z, then logistic regression is 1 plus e to the minus z. So sigmoid is this, right? That is it. And as you can see, this belongs to the interval 0 to 1. It's a probability basically. So you can tell the probability that it will win, right? The strong model will win. Likewise, or the weak model will win. Pick one. Likewise, you can do something different. That was using the encoder model. Remember, BERT is an encoder model. There is yet another approach, a third approach, I believe, or fourth approach that they suggest, which is to use a causal LLM. What about a decoder model? So if you take a decoder model, which is practically making the router itself a little LLM, what will you have to do? You will have to give it an instruction, something like, will this query queue be much better? Let's say, I'm just cooking it up. I haven't checked the exact query. Much better answered by the stronger model. Answer as yes, tie, no, or something like this. Make it choose one of them. So you can use the answer to that, isn't it? So you can literally take a decoder model, like basically a causal LLM, as your routing network and make it do that. So there are 4 methods: the statistical method, matrix factorization, using an encoder, BERT encoder, or using a decoder like a causal LLM, right? And giving it a prompt and just saying, tell me what it is, giving it an instruction. They do the experiment. Suffices to say that the experiments convincingly show you that you can save a lot of money. Go ahead. Oh, yeah. No, it is. It's the router. So see, you have, so again, just to whet your recollection, remember what we said. There is the router. There is the query going in, and it has to route to big LLM or to tiny LLM. Isn't it? That's the thing. So we are only talking about this guy. And what we are saying is the router network, router can be as one of 3 methods. A, statistical method, the similarity one. Similarity. B, the recommended system kind of approach, matrix factorization. C, using encoder, and D, using a decoder, right? So I'll just put it. See, if you're using a transformer, you don't have too many choices, right? So you'll use a causal LLM. I suppose there was a E choice, use a full transformer, encoder, decoder, all put together, right? You could have done that. You could have used, for example, flan T5 or something like that, T5 or something, right? But they didn't go with those 4 choices. But we are talking about how would you now do this magical router? You have 4 choices. So then it goes into the benchmarks. And at the end of this, as you would imagine, the reason this paper gained attention from a practical perspective is because it showed that this is a good practical strategy. You can actually reduce your cost by a huge magnitude by using it. So by the way, this is the first work, I would imagine, if I have to guesstimate, now that this result has been proven that this approach works, there will be subsequently a lot more research done to go from what looks like a first round approaches to more sophisticated approaches in subsequent papers. I'm guessing, huh? Because these things have a tremendous amount of practical implications. We are talking about real expenditure here, right? And viability or feasibility of things, of using LLMs in-house and the cost we pay for that, right? So with that, I'll end the formal part of the presentation. So let me see if usually there's some nice things to say. So this kinds of curves always remind me of the area under ROC curve or ROC curve kind of thing. If you remember that if you just make in the random choices in a binary classifier, do you guys remember that a random choice, a classifier that's basically useless, a binary classifier that's useless, does it look like a line like this, right? And anything better should be a line above it, right? So obviously matrix factorization and causal models are both doing very well. And they go on to show many such results. But anyway, I will end with the conclusion. So in conclusion, they say, we demonstrate strong routing performance by our routers across a variety of benchmarks spanning open-ended question answering, humanities, and math problems. By intelligently routing queries between a strong model and a weak model, our routers are able to achieve significant cost savings while maintaining a high response quality. So that is the result. They successfully created a router. Our routers are able to achieve significant cost savings while maintaining a high response quality. Doesn't mean that you don't lose some. You lose a little bit, but does it matter in practical terms? You have to judge. And based on that, you can set your threshold, your cost threshold. How much are you willing to spend for that extra bit? Our results also highlight the effectiveness of dataset augmentation in improving router performance while training routers solely on the blah, blah, blah. So these things we'll skip. That it's always helpful to have more data. Then they mention their limitations. They say, while our work demonstrates strong results, there are a few limitations. First, although we evaluate on a diverse set of benchmarks, real-world applications may have distributions that differ substantially from this benchmark. See, that is real. All they have proven is at least for this data set, if you train, then on these benchmarks, this router works. They acknowledge the fact that if you have a substantially different data distribution in real life situation, this router may not work. And that is nice. So to this end, we show that users can collect a small amount of in-domain data to improve performance for their specific use cases via data augmentation. So what they say is that there is a way out. You go gather your own data, go train it. The other thing they observed, which I forgot to mention, they found that they tried it with one big LLM and one small. They got good results. And then they did a form of transfer learning. They replaced the big LLM with a completely different big LLM and the small LLM with a completely different small LLM. And much of the results still worked. So it is something that gives you confidence that not only is that learning transferred, but also likely this result is more robust, is relatively robust. It isn't that it only works for this specific situation. Right? And so that's the value of this paper. All right, guys. So any questions that you would like to ask on record? Otherwise, I'll stop the recording.